Another type of angle that can be formed through segments drawn on a circle is the inscribed angle. Specifically, it can be formed when two chords intersect on a single point on the circle. There are four chords on the figure named as segment DA, segment CA, segment DB, and segment CB, wherein we can deduce that there are four angles, which are angle DAC, angle DBC, angle ACB, and angle ADB. Angle DAB and angle DBC intercept arcs DC, while angle ACB and angle ADB intercept arc AB. Just like the central angle, the measure of an inscribed angle can be determined by its intercepted arc. The following theorems will tell us how the measure of an inscribed angle is related to the measure of the intercepted arc. Inscribed angle theorem. The measure of an inscribed angle is 1/2 the degree measure of its intercepted arc. Using the figure, we have angle APC as an inscribed angle, intercepting arc AC. With the inscribed angle theorem, measure of angle APC is equal to 1/2 the measure of arc AC. Let us take a look at these examples. Refer to the figure on the right to answer the following. A. If measure of angle CBD is equal to 54, what is the measure of arc CD? And B. If measure of arc AB is equal to 96, what is the measure of angle ACB? On the figure, angle CBD intercepts arc CD. Therefore, to solve for the measure of arc CD, the idea of the inscribed angle theorem will be applied. The measure of the arc CD is twice the measure of angle CBD. Therefore, measure of arc CD is equal to 108. Solving for the second problem, if measure of arc AB equals 96, what is the measure of angle ACB? Angle ACB is an inscribed angle intercepting arc AB. Therefore, its measure is half the measure of arc AB. Hence, the measure of angle ACB is equal to 48. Since the idea of the inscribed angle theorem has been cleared using the previous examples, we can now move on to the next set of theorems about inscribed angle. Corollary number 1. An angle inscribed in a semicircle is a right angle. On the figure, angle NTE is inscribed in a semicircle. Using the idea of the inscribed angle theorem, the measure of the angle is 1/2 of the measure of the semicircle, giving us 90 degrees as the measure of angle NTE. Therefore, angle NTE is a right angle. Corollary number 2. Two or more angles inscribed in the same arc are congruent. On the figure, angle PIE and angle PLE are both inscribed in arc PE. Therefore, angle PIE is congruent to angle PLE, meaning to say the measures of angle PIE is equal to the measure of angle PLE. Let us take a look at this example. What is the measure of arc AD in figure 5.10 given that the measure of angle ABD equals 5x plus 3 and the measure of angle DCA is equal to 4x plus 10? Solving for x, we will be equating the measure of angle ABD and the measure of angle DCA. Then substitute the given. Combining like terms, we will come up with 5x minus 4x is equal to 10 minus 3, giving us x is equal to 7. Since we already have the value of x, we can now solve for the measure of arc AD using either the inscribed angle ABD or angle DCA, since they are congruent. We will be applying the inscribed angle theorem. Using the measure of angle ABD, we have the measure of angle ABD equals to 1/2 of the measure of arc AD. Substituting 7 to x, we will have 4 times 7 plus 10 is equal to 1/2 times the measure of arc AD. Combining like terms, we will have 38 is equal to 1/2 the measure of arc AD, giving us the measure of the arc equal to 76. Corollary number 3. Opposite angles of an inscribed equilateral are supplementary. On the figure, we have quadrilateral QUAD, wherein pairs of opposite angles are angle U and angle D, and angle Q and angle A. Based on the corollary, we may say that the measure of angle U plus the measure of angle D is equal to 180. Likewise, measure of angle Q plus measure of angle A is equal to 180. Example number 6. Given the figure below, with the measure of angle K and L equals 65 and the measure of angle L and M equals 45, what is the measure of angle KLM? Angle KLM and angle KNM are supplementary angles since they are opposite angles of the inscribed quadrilateral KLMN. Also, take note that the measure of angle K and M is equal to the measure of the two given angles K and L and angle L and M. Therefore, the working equation will be the measure of angle KLM plus the measure of angle KNM equals 180. That is applying corollary number 3. Substituting the given, we will now have the measure of angle KLM plus the measure of angle KNL and LNM, which are 65 and 45, equals 180. Combining like terms, we will have the measure of angle KLM is equal to 180 minus 110, giving us the measure of the known angle, which is equal to 70. Next set of theorems will now be about the chords of a circle. For any chord which is not a diameter, there is a minor arc having the same endpoints. In figure 5.12, the chord BA corresponds to arc BA. This idea will be the starting point of the theorems on chords that will be discussed further. Chord arc congruence theorem. In a circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Given circle P and circle Q which are congruent, arc AB is congruent to arc CD if and only if segment AB is congruent to segment CD. Likewise, given circle Q, wherein arc EF is congruent to arc CD, in circle Q, arc EF is congruent to arc CD if and only if segment EF is congruent to segment CD. Perpendicular to a chord theorem. A line through the center of a circle bisects a chord if and only if it is perpendicular to the chord. On the figure, segment BG is congruent to segment AG if and only if line KL is perpendicular to segment BA. Also, arc BL is congruent to arc AL if and only if line KL is perpendicular to segment BA. Distance chord theorem. In a circle, two chords are congruent if and only if they have the same distance from the center. On the figure, segment CD and segment EF are chords of the circle. They are congruent if and only if segment HQ is congruent to segment JQ. Example: in the figure, R and U are the foot of the perpendicular segments from the center O to the chords. If PQ is equal to 14 and OR is equal to OU, find SU. Find the radius if segment ST has the length 24 and is 9 units away from the center. On the first problem, the unknown is the length of segment SU. Since segment PQ and segment ST are of equal distance from the center O, by distance chord theorem, these two chords are congruent. Subsequently, SU is equal to 7 because of the perpendicular to a chord theorem. Since PQ is 14 and ST is congruent to PQ, SU is just half of ST, which is equal to 7. On the second problem, the unknown is the length of the radius segment ST. Given that segment OU is perpendicular to segment ST, these two segments form a right angle along with the radius of the circle. With these, two right triangles, triangle OUS and triangle OUT, are formed, suggesting that the Pythagorean theorem will be applied. Focusing on triangle OUS, we can solve for the unknown through the Pythagorean theorem. The legs of the triangles are SU, which is 12 units, OU, which is 9 units, and the unknown is the other side of the triangle, which is the hypotenuse, SO. The working equation will be the square of the length of the hypotenuse is equal to the sum of the squares of the length of the two legs, which is SO squared is equal to SU squared plus OU squared. Substituting the values of SU and OU,